Welcome to the Explainer. Today, we're going to decode the secret language that powers, well, pretty much everything in our digital world.
All right, let's kick things off with a mystery that is quite literally right at your fingertips. I mean, think about it. How can a simple switch, something that's only ever on or off, create everything? We're talking video games, complex spreadsheets, the photos on your phone, the music you stream, all of it. It seems impossible, right? But the answer is that our entire digital universe is built on this incredibly simple two-state system.
And to make the system work, we just need a way to label those two states. So we give them a number, 1 for on and 0 for off. Simple as that.
This two-digit system, this language of ones and zeros, has a name. We call it binary. You can literally think of it as the native language of every single computer on the planet. Just like you and I think in words, computers think in these long strings of ones and zeros.
So, why binary? Why this super simple system?
Well, what's really fascinating here is that using just two digits isn't only about making things easy. It is incredibly efficient. Because the calculations are so basic, right? Just ones and zeros, computers can be built with way less circuitry. And that creates this amazing domino effect. You need less physical space for hardware, which means lower energy use, and at the end of the day, it all costs less. It's the ultimate example of less is more.
Okay, so to really get our heads around binary, we actually need to take a step back and look at the number system we all use every single day, probably without ever thinking twice about it.
When you see a number like 345, you know what it means, instantly. But there's actually a hidden structure inside of it, a secret code that we all learned back in elementary school and then kind of forgot about.
See, it's not just a 3, a 4, and a 5. Each digit's position gives it a totally different weight. The 5 is in the ones place, the 4 is in the tens place, and the 3 is in the hundreds place. All of this is based on powers of 10. And that's the hidden logic of our everyday base 10 system.
So what we're really talking about here is something called a number system. And that's just a fancy way of saying a set of rules for counting. The system we've used our whole lives, that's base 10. It's called that because, well, it uses 10 digits, 0 all the way up to 9. But here's the mind-blowing part. Base 10 is just one way to do things. It's just one option out of many.
And this table shows it perfectly. There are tons of other systems. You've got octal, which is base 8, and then there's hexadecimal, or base 16, which is so big it actually runs out of numbers and has to start using letters. A, B, C, D, E, and F. Now we'll get back to why on earth we'd need something like hexadecimal in a bit, but the main point for now is this. You can build a totally logical, perfectly functional number system using almost any number of digits as your base.
Okay, so if all these different number languages exist, how do we translate between them? Let's tackle that right now. Let's figure out how to convert the computer's language, binary, back into something we can understand. Our good old base 10.
And lucky for us, there's a simple, universal, 4-step method for this. It's called power expansion, and the cool thing is it works for converting any base back into our familiar base 10. Let's walk through it together.
All right, we're going to use this binary number as our test subject, 1101. Now, you'll often see this little 2 written as a subscript next to it. That's not part of the number. It's just a little tag to remind everyone, hey, this is a base 2 number, so you don't mistake it for 1101.
Okay, so step 1. Remember how our number system has the ones place, the tens place, the hundreds place? Well, binary has the exact same thing. But, and this is the key, instead of being based on powers of 10, it's all about powers of 2. And you always start from the right. The first spot is 2 to the power of 0. The next is 2 to the power of 1, then 2 squared, and you just keep going for as many digits as you've got.
Now for the easy part. You just multiply each digit in the binary number by the place value that's sitting right above it. So we take our first 1 and multiply it by 2 cubed. Then the next one gets multiplied by 2 squared. You get the idea. We just go right down the line. Once you calculate all those little multiplication problems, you're left with a super simple addition. We've got an 8, a 4, a 0, and a 1. All we have to do is add them up. And there it is. Add them together, and you get 13. So that binary number, 1101, is just the computer's way of writing 13. See, it's not a different amount of stuff. It's just a totally different language for describing it. Okay, that's cool. So we can translate numbers back and forth. But can you do actual math in another base? Like, could you add two binary numbers together? The answer is absolutely. And what's wild is that the logic is going to feel surprisingly familiar.
All right, let's take a look at this binary addition problem. I know, it might look kind of weird at first glance, but I promise you, the fundamental logic is exactly the same as the addition you learned as a kid.
Here's the one and only trick you need to remember. In our everyday base 10 system, what happens when a column adds up to 10? You write a 0, and you carry the 1 over to the next column, right? Well, in binary, the magic number isn't 10, it's 2, because it's base 2. So if a column adds up to 2, you do the exact same thing. You write a 0 and you carry the 1. That's literally the only new rule.
So if you just apply that simple carry the one rule every single time a column adds up to 2, you can solve this thing, just going step by step from right to left. It's almost like a little puzzle. And if you follow that one rule, you get your final answer 1100110. It just goes to show you math is a universal language. It doesn't matter what base you're using.
Okay, look, this is all really cool from a pure math perspective, I get it. But what's the practical point? I mean, if computers only speak binary, and we humans are perfectly happy with our decimal system, why on earth do we need to bother with anything else? Remember that weird hexadecimal system with the letters we saw earlier? What's that for?
And here's the crucial takeaway. Each of these number systems is like a specialized tool for a very specific job. Binary, that's the raw, fundamental language for the computer hardware. Denary, our base 10, that's for us, for everyday human communication. And hexadecimal, that's the genius bridge between our world and the computer's world. It works as a super convenient shorthand that lets human programmers read and write these massive, overwhelming strings of binary code without losing their minds. Each one has its perfect role to play.
So when you start to understand number bases, you uncover this hidden logic, this beautiful, elegant simplicity that's sitting right at the heart of all our complex technology. And it kind of makes you wonder, doesn't it? What other powerful, elegant systems are out there, quietly running our world, just waiting for us to notice them and decode their language?